All right, great. So thank you, everyone, for taking the time to join. I'm going to present on Berkeley Lab technologies and licensing. My presentation will have three components. The first will be just an overview of Berkeley Lab to familiarize the audience with Berkeley Lab and kind of the background and what we work on. I'll then talk about a couple of sample technologies that I think should be relatable or interesting audience. Then I'll talk a little bit about how Berkeley Lab works with industry and other partners, both from a licensing of existing IP standpoint, and then also from a potential collaboration. We have a lot of very good resources, as does Idaho, as does NETL. But I'll talk a little bit about kind of the mechanism, possibilities for working. So get that slide, overview of Berkeley Lab. So just a little bit on Berkeley Lab. It's known as the home of team science. It was founded in 1931. It was the first national lab, and it was founded by Ernest Lawrence, who was a high-energy particle physicist who basically developed the idea of atom smashing. A couple of fast facts, like some of the other national labs, we are owned by the Department of Energy. We've got $800 million some odd budget, about staff of about 4,000, but somewhat uniquely within the national lab network, we're operated by the University of California. So that gives us some advantages in the sense that we have access to the University of California resources. A lot of our scientists are also professors at UC Berkeley, so you get kind of the best of both worlds. You get access to world-class, scientists and postdocs and grad students that only Department of Energy National Labs can offer. A history of strong science, 12 Nobel Prizes from Lawrence to Seaborg to Macmillan for transuranic elements, Calvin for photosynthesis, and more recently Perlmutter, who are doing astrophysics. To highlight some of the ceramics that I described, about 14 elements were discovered or synthesized at Berkeley Lab by Lawrence, by Seaborg. Actually, quite a few are named after Berkeley Lab. There's americium, berkelium, californium, francium, borgium. All of those are all, those names derived from the relationship they have to Berkeley Lab. A couple of other interesting kind of historical technologies are around imaging single atoms. There's a team at Berkeley Lab has developed something called a transmission electron aberration corrected microscope. So it's basically a TEM with an extra A, the aberration correction, and that allows scientists to image down to single atoms. And some work recently around tomography that allowed scientists to map, I think, about 23,000 atoms within a nanocrystal, exact location of every atom. And, as I mentioned, a lot of breakthroughs. Now a little bit about, the lab today. So the lab has 6 research fields. They're called lab areas, and they range from biosciences to computing sciences to earth and environmental sciences. I think for today's focus, I'll talk mostly about earth and environmental sciences and the physical sciences, because those are the homes of the well sampling, modeling, oil and gas modeling simulators, and also some of the neutron generators and radiation mapping that I think is most relevant. So, with that in mind, I mentioned there's the Earth and Environmental Sciences area. That is the home to our first 2 sample technologies. So, one of the prior speakers talked about codes for understanding geophysics. And the tough codes are another set of codes that do that. And there's a description on the slide that I won't read verbatim. But the idea is to model the transport of water and gas and oil and CO2 and brine and other liquids and gases and fluids overall within porous media, porous and fractured media. So there are a lot of different applications for this. Everything from geothermal, understanding a geothermal resource, what the lifetime might be, what the quality of heat might be, to oil and gas reservoirs, geological carbon sequestration, hydrology, subsurface water reservoirs and the dynamics within them. So there are a lot of potential applications. These tough codes are world-class, and they've been licensed upward of 500 or 600 times to a combination of academic institutions, commercial institutions, oil and gas, geothermal, water conservation and water management. So in terms of IP and the availability, software packages that are available for non-exclusive licensing. There's a website. It's very easy to find, TUF and LBL, and it should be the first result that on the slide. But if you want to learn more, certainly contact me, or you can take it there for some more technical reasons. So those are the TUF codes, essentially, a simulation tool for understanding the geophysical environment, and it's got a lot of applicability, and it's been actually applied in practice, a lot of different industries and all. The next technology is a well characterization technology. So the idea is to characterize, environment around a borehole. And I've put on here a specific example of a way to basically sample the fluid and the rock around a borehole without, basically in a simplified way. So this is a patent application that's available for licensing. Another technology that I didn't put on here is for well characterization is actually based on nuclear magnetic resonance. There's a very prominent research group at the lab that is expert in magnetic resonance, and they've actually developed a downhole device that can be used to understand the chemical composition within meters of the borehole, as opposed to in centimeters, which I think is more common. So it's a very penetrative technique. So what I've shown here, and also that NMR, nuclear magnetic resonance, are a couple of the different well characterization technologies that have been developed in the earth and environmental sciences area. So next is switching over to the kind of the physical sciences area of the lab. This is where we do a lot of the it's kind of the successor to the original work of the lab, which was atom smashing and physics. So we have a very prominent group in developing neutron generators, and neutrons are very useful for characterizing materials, examining the different parameters of geological formations, for example, in borehole logging, soil porosity, etc. There are a lot of other applications in the medical field, in security that can use neutron generators. We have a very large portfolio of neutron generator designs. Obviously, the one that's most applicable in a given application will be determined by a number of factors: size of the generator, the energy of the neutrons that are produced, the flux of the neutrons. But we do have a large portfolio, something on the order of 50, 20 different designs by a very prolific research at the lab. So, if you have need for a neutron generator, it's likely that you have a design and IP that can achieve characteristics of the performance that you're looking for. So the last technology that I'll highlight is radiation mapping. So working with a lot of radioactive materials, there's a very big research group at the lab that has developed tools for mapping the radiative environment. And what you can see here is it's essentially a handheld or drone. It can be added to a drone or equipped on a drone. It's essentially a tool for overlaying physical environment with the ionizing radiation environment, specifically gamma rays. So, for those of you familiar with, self-driving cars or unmanned vehicles of some kind, you use LiDAR to map out the physical environment, and then this technology pairs that LiDAR image of the physical environment with an image of basically the radiative or ionizing radiation environment. And so it's a tool for identifying and localizing radioactive sources in near real time. The example photos that I've included were this technology being used in the Fukushima nuclear power plant and surrounding countryside. Imagine from the fallout, there's been a lot of contamination over a large area. And so a big question is, where are the radiation hotspots? Where is the contamination that we need to neutralize or to remediate? And so the technology that I'm describing that overlays the physical environment and the ionizing radiation environment deployed there. And the two images that you see there are the two pairs of images are the physical environment and then the radiative environment with the LiDAR-based physical environment representation. So this is it's a technology that can be used in a lot of different applications, from security to disaster, disaster zones. And the IP and availability, we have hardware and software copyrights available for licensing wide. So those four technologies that I just mentioned were the sample technologies that I thought was most relevant to this. Tough codes for simulation of oil and gas, of geothermal, of hydrology. So that's a simulation tool, a tool for physically characterizing boreholes and wells on kind of the oil and gas and fuel side. And then there's neutron generators, radiation mapping, nuclear and radiative side. So those are the sample technologies, and I'll spend a little bit of time talking about how you might work with Berkeley Lab if you're interested in some of the software or technologies that I just described, or maybe getting access to some of the resources that it has. So the technologies, those four, are all indexed and searchable at the IPO website. I probably should have mentioned this earlier. The Innovation and Partnerships Office is basically Berkeley Lab's office for interfacing with industry and non-Department of Energy functions. So the technologies that the lab has developed are all indexed and searchable on that website. We've had a lot of success licensing our technologies out. On the slide, you can see a lot of the different partners that we've worked with. From a licensing standpoint, so pushing out the technologies that have already been developed, we have a couple of different agreements. We have option agreement, which is essentially a exclusive negotiating period. Set the technology aside, only you, your institution, are allowed to negotiate with us in faith for an eventual license. And the option agreement is often good for doing diligence. You don't want to commit the capital to a full license. You want to do diligence, understand the technical and market risks and possibilities. Option is that. and then, of course, a full license allows one to practice the invention. Our terms are probably pretty standard within the Department of Energy National Lab community. So if you've worked with the National Lab before, nothing that we do will be very surprising. So, as I mentioned on the right here, you can kind of think of this as organizations looking for an idea or opportunity. Obviously, we have intellectual property, IP portfolio agreements, and then partnerships. And then if you have an idea or you want to collaborate with the lab, there are different ways to do that. Two are a cooperative R&D agreement, partnerships program, which is formally called the Work for Others program. Those are a couple of different mechanisms for collaborating with lab scientists and getting access to lab resources. And Berkeley Lab also has something called user facilities, which are, you can see 3 examples here. They're basically advanced research facilities where an industrial or academic partner can come to the lab and use the resources, the equipment, the expertise. So there is basically a proposal process for that, and it's merit-based on the scientific, or it's evaluated based on the scientific merit of the proposal, but assuming that there is some scientific merit to what you're proposing, resources and scientific expertise offered for free. That's a pretty popular choice, as you can probably imagine. And then the 3 here, the Advanced Light Source Foundry and Genome Institute, mostly the Advanced Light Source and the Foundry, those are primarily for experimental research. So things like developing neutron generators or well characterization techniques, developing new materials, characterizing new materials. And then we have some use high performance. So NERSC on the right, the National Energy Scientific Computer, that is the supercomputer at Berkeley Lab. And when people run the tough codes that I described earlier, the calculating oil and gas and geothermal and the like, they will often run it on NERSC and get answers within days, hours to days. One example that I should have mentioned is the Aliso Canyon leak that happened. Expertise and the software developed at Berkeley Lab, the tough codes, was actually used plugging that leak. There are 3 or 4 attempts over the course of several months to be plugged. LBL and the tough developers and the tough codes were brought in, and they had a solution within a week. So that's the kind of the usefulness and the compute power that Berkeley Lab offers. So that's the last slide that I have. I'm not sure if we take questions or if I should. Yep, I don't think I have any questions right now, so I can pass it back to Aaron.